Hey guys, hope everybody's doing okay. What we're going to do right now is take a look at an introductory lesson for our acid-base equilibrium unit, which is going to focus on strengths of acids and bases and things called Ka and Kb values, in addition to conjugate acid-base pairs. So let's get started and take a look at some of this. We're going to start with defining what a strong acid is. So a strong acid, or really the strength of any acid, depends on how much it dissociates in water. Okay, so we did talk about this a little bit in Chem 1. Here we have a generic acid, usually written as HA. All right, acids start with H, and they have some anion, right? So like HCl, HF, H2SO4, right? That negative ion is the A, and the H is obviously your hydrogen. So if we have something like this, we have generic acid HA. Relative number of moles is here. Okay, so some amount of moles of acid is being placed in water. Look what happens. Once you mix it with water, it dissociates, okay? And you have none of the HA left at all. It is completely dissociated into its ions, all right? So let's take a look at an equation for this. HA is your acid plus water, liquid, yields H3O plus your hydronium ion plus your conjugate base A minus. All right, this is one way to write this. You'll see it written like this, or you'll see it written an alternate way where you may not see the H2O here, and you'll just have HA, and then you'll have yields instead of H3O, you'll have H plus, okay, plus A minus. All right, so sometimes it's written this way. Sometimes it's written with the water. You should be familiar with it either way. The thing I want you to understand is that H plus and H3O plus are basically equivalent. All right, they mean the same. They basically mean the same thing. It's your H plus ion or H3O plus ion. Okay, so a strong acid is going to dissociate completely in water, and you're going to be left with, all of the HA will break up and dissociate into H plus and A minus. Since we have a 1-to-1 ratio right here, then we break up into a 1-to-1 ratio with our ions here. So if we had, 3 moles of HA at the end after dissociation, 3 moles of H plus, 3 moles of A minus. Note the full arrow to the right, the full yield sign, because we went completely to the right, full dissociation, so you could be familiar with that for strong acids. All right, you won't see the equilibrium sign there. If you look at initial and final molarity values here, it's basically what I had in the last slide. There's your generic equation. See how I shortened it up here on this slide? So here's your dissociation of HA without the H2O written in there. Okay, I also have it right here, what it can be written as, so I went over this already. I have my initial concentrations of all of my substances. So I said 3 molar on the last slide, HA, 0 molar and 0 molar of your ions, because you didn't dissociate yet. Obviously, a change occurs, and at equilibrium, what are you going to end up with if it's complete dissociation? You're going to have no HA left, and because it's a 1-to-1 ratio, you have 3 molar and 3 molar. So the KEQ for an acid dissociation is called Ka. So if you go back to last unit, we had KEQ values, and that basically told us, are we reactant or product favored? This is the same exact thing, except if we know we have an acid to start with, we could just make our equilibrium constant value something called Ka, so we know we're dealing with an acid. So for something like this, the Ka expression is written as follows. It's the exact same way we would have written them back in Unit 3. So Ka is the concentration of H plus times A minus over HA. And for a reaction like this, you have to think about what would be true for this. This is a reaction that goes completely to the right. So if a reaction lies basically 100% to the right, we know that our Ka value should be really big and way greater than 1. Okay? So that is for a strong acid. Now let's take a look at weak acids. Generic weak acid, HA, right here. Once you mix it with water and it dissociates, look how much dissociated. Hardly any, if I draw a straight line over here. A little bit. So a little bit of our HA broke apart into H plus and A minus ions. So let's say we started with 3 molar of HA. We might end up with 2.9 molar HA. And then this would be like 0.1 and 0.1. Okay? So weak acids are not going to dissociate very well in water. That's what defines a weak acid. So if you're wondering what's the difference between strong and weak acids, this is definite foundational knowledge you need to know about that. Notice the equilibrium, or the equation, looks basically the same here. The only difference is we have this equilibrium sign, okay? Because we didn't go fully to the right, we only went a little bit to the right. So you have basically this HA breaking up into H plus and A minus, and then it's in equilibrium. So some of this HA will break up, and some of this A minus and H will reform to make HA. It'll be equilibrium back and forth into dissociate, not dissociate, dissociate, not dissociate, and go from there. So let's take a look at what our table would look like for this. Weak acids dissociate very slightly, like I already mentioned. So here are your two equations. Notice, again, they're exactly like before, except we have an equilibrium sign here now. Initial equilibrium, or initial concentration of HA, 3 molar, 0 and 0 for H plus and A minus. Then at equilibrium, about 3 molar. No, it's a little less than 3 molar. Then I have 0.004, 0.004. I don't know what it is. This is just a generic weak acid I'm just using random numbers here for. But you find the Ka expression the same way. And if you look at the Keq or Ka for this, notice that we had 3 molar to start with for HA, and we have a little less than 3 molar to end with. So we're very, very reactant favored here. So for weak acids, you should note that the Ka is going to be way less than 1. All right? So that takes care of strong and weak acids, basically. It's the level of dissociation for the two of those. So in summary, the lower the Ka, if we go back here, the lower the Ka, the weaker the acid is going to be. It's the same idea for bases. Bases are going to dissociate and produce hydroxide. Okay, so if we want to write a dissociation equation for bases, you could just put your NaOH yields Na plus OH minus. Strong bases will completely dissociate, and weak bases will only partially dissociate. So the higher the Kb value, the stronger the base is going to be. These are called Kb values, okay? Because if you're dissociating a base, B for base, Kb. So don't let the Ka and Kb fool you. It just basically is telling you what you're starting with, an acid or a base. Pay attention to them though. They're obviously not interchangeable. If a problem gives you Ka or Kb, you have to know that you're starting with an acid or a base, and you'll go through your dissociation equation based on what you're starting with there. All right? You have to memorize the common 7 strong acids. So it's HCl, HBr, HI. Those are all in the halogen group, HCl, Br, and I. Then you have some very common acids here, nitric acid, sulfuric acid, chloric, and perchloric. All right, so HCl, HBr, HI, HNO3, H2SO4, HCl3, HClO4. You need to memorize those. All right. All of these are going to have a Ka value of way bigger than 1. All right. Basically, if it's not in this list, your Ka value would be less than 1. You consider it a weak acid. All right. So these are your 7 strong. Ka value is way greater than 1. Anything else, Ka value less than 1, weak acid. So here's there's a million of them here. Here's a list for you. This is the same list that's in your textbook, I believe, should be in your packet. So here are your Ka values for a bunch of acids, and it asks you which of the acids is the strongest. So based on the last slide, we said the larger the Ka value, the stronger the acid is going to be. So in this case, iodic, HiO3, is the strongest, and HiO, hypoiodous acid, is 2.3 times 10 to the negative 11th. That is the weakest. So acid strength is going to decrease going down the table, which means smaller Ka value. Another table shows you a base along with the acid. All right. So we have strong acids. Okay, here's some of our, here's 4 of our top 7, right, that we had on the previous slide there. You want to look at what we have over here on the right. We have something called a conjugate base. I haven't really defined that yet. I will in the next slide or two. But you have an acid, HClO4. If you lose the hydrogen, you end up with ClO4. That's actually a base. Okay, so the relationship I want you to see here is that if you have a really strong acid, the stronger the acid, the weaker the conjugate base is going to be. All right, so HCl is a strong acid. We know that. It's one of our top 7. If it dissociates, you make Cl minus. Cl minus will act like a base. That's actually, it'll act like a Bronsted base, right? It'll be a proton acceptor. We learned about that back in Chem 1, and we should review that before this lesson here. This Cl minus is not going to be a very good proton acceptor, okay? So it's a very, very weak base. We call this the conjugate base, all right? HCl is your acid, Cl minus is your conjugate base. So look at the relationship here. Strong acids have weak, very weak conjugate bases. Weak acids will also have weak conjugate bases. And then really strong bases are going to have really weak conjugate acids. Okay? So if something is strong, the conjugate is weak. If something is weak, the conjugate is weak. And it doesn't make too much sense. When we learn more, it will. Okay? So look at our example here for conjugate acid-base pairs. We have HNO2 plus H2O yields NO2 minus and H3O plus. So identify the acid and base in the forward reaction is what we want to do. So this is really, really, really easy. In the forward reaction, that's the reaction going left to right, identify the acid and base. So you have HNO2 plus H2O. And on the product side, you have NO2 minus. So that means that HNO2 lost that hydrogen. Well, where did it go? It donated it to H2O because now we've created H3O plus. So HNO2 is our proton donor. H2O is our proton acceptor. That right there defines the acid and base for us. Okay, so HNO2 in the forward reaction is the acid, donates the H plus to NO2. Or to form NO2 minus, I should say, and it donates it to H2O, which is our base, our proton acceptor, to create H3O plus. All right, it accepts that hydrogen. Okay, so we've done that before. There's nothing new here at all. What we need to do now, though, is look at the reverse reaction. We never had to do that before. In the reverse reaction, since it's an equilibrium system, we have an acid and base in the reverse direction. So this is really easy. All you want to do is look at the reverse direction, the reverse reaction, and figure out what's your proton donor and proton acceptor. Well, if the reaction is going right to left, here's H3O plus. It's creating H2O. So H3O plus to H2O, it's losing that hydrogen. Where is it going? Well, it's going to the nitrite ion because we're making HNO2. So in the reverse direction, the H3O is your acid, and the NO2 minus is your base. Okay, so in the reverse direction, though, we call it a conjugate. So there's our conjugate base. It gains a proton in the reverse direction, reverse reaction. And H3O plus is our conjugate acid. Okay, it's donating a proton in the reverse direction. So after an acid loses hydrogen, what's left is a base. We call it the conjugate. After a base gains a hydrogen, like H2O did, it creates H3O plus. We call that the conjugate acid. All right, so pretty easy to find these. HNO2 acid, NO2 minus, conjugate base. H2O base, H3O plus, conjugate acid. All right, so they're really going to differ by a hydrogen. That's really all it is. Okay, guys? So back to what I had on a few slides ago. Now that we know a little bit more about what a conjugate acid base is, the stronger the acid, like I had here, okay, the stronger the acid, the weaker the conjugate base is going to be. All right? So strong acid will have a weak conjugate base. But again, look, a weak acid is going to have a weak conjugate base because there's no dissociation here. It's not a lot of dissociation. So it'll work the same in both directions here. Okay? H2S, HSO3 minus, aren't going to want to dissociate very well at all, making them weak acids. And their conjugate base, HS minus, SO3, negative 2, they're not going to want to act very basic here at all either because they're coming from a weak acid. All right, so weak acids, weak conjugate bases, but strong acid, very, very weak, negligible conjugate base. If you're trying to figure out what way a reaction is going to go, if you have one of these systems, you want to find out where the weaker base is. Okay, so a rule of thumb here is that equilibrium will lie on the side with the weaker base. If you have some more information like Ka and Kb values, you could figure it out that way too. But if you're just looking at it something like this, you could easily figure out, like in this first reaction here, what side does equilibrium lie on. So you know hydroxide is a very strong base, right? And that's what makes a lot of things basic, is that OH ion. And then over here, you know that NH3, like we know that's a base from Chem 1, and we know it's weak. All right, it's a weak base. It's ammonia, so that's going to be where equilibrium is going to lie. Equilibrium will lie on the side of the weaker base. Your weaker base is right here, and look at the equilibrium arrow. It is shifting a little more to the right, so equilibrium lies to the right over here. So Kc would be greater than 1. Yeah, Kc would be, because it's even acid and a base here. So Kc is greater than 1. If you look at the other reaction, HF is a very weak acid. It's not one of our top 7, but H3O is basically the hydrogen ion, so that's very strong. So equilibrium will lie over here. It will lie to the left. So you could look at your bases then. All right. So if this is a very, very weak base, or sorry, very, very weak acid, this is a little bit stronger conjugate base. Okay. So I'll put conjugate base here. Okay, it's a little bit stronger. But look, you have a really strong acid over here. So this H2O is a very, 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 very weak base. All right. So the very, very weak base is going to be weaker than just the regular conjugate base here, F minus. So equilibrium lies to the left. Okay. So find your weaker base. That's where equilibrium is going to lie. So Kc less than 1. Okay, this reaction, you could identify the conjugate acid-base pair, identify it as strong or weak, and then predict whether Kc is less than or greater than 1 or about 1. Okay, so I'll give you a second to do that. We'll pause the video if you want to. Okay, so HNO3 plus NH3 gives you NO3 minus NH4 plus. HNO3 looks like it's donating a hydrogen, so this is going to be acidic. That would make NH3 the proton acceptor, which is a base. And then once the HNO3 loses the hydrogen, you have a conjugate base. All right. And you have a conjugate acid right here. All right, because that's what gained your hydrogen. So identify the conjugate acid-base pairs. We did that. So there's your acid conjugate base and your base and your conjugate acid. That's done. Identify each as strong or weak. Okay, so let's do that. So this is definitely one of our top 7 strong acids. So the conjugate base is going to be very weak. Okay, your base, NH3, is definitely weak. Talked about that in the last slide. So your conjugate acid will be weak. Simple. Predict whether Kc is less than 1, greater than 1, or about 1. So for this, we need to look at our 2 bases here. So it's NH3 and NO3 minus 1. Which one's weaker? Well, your strong acid is HNO3. That makes this NO3 minus extremely weak. Kind of like if you look at the charts, it says negligible. So extremely weak, negligible conjugate base would be a little bit weaker than the NH3. Okay, so, maybe a lot weaker than that. So equilibrium is going to lie to the right. Okay, because the NO3 is negligible compared to the NH3. So that means Kc is greater than 1. All right, that takes care of that. Next thing we need to do here is write expressions for the dissociation of these various things. So we have nitric acid. Your dissociation equation looks like this. HNO3 yields H plus plus NO3 minus. And the equilibrium expression will look like this. Ka is H plus times NO3 minus over HNO3. This is nothing different than previous problems we did in Unit 3. Calcium hydroxide, though, is a solid. Look at your dissociation equation there. This goes back to what we did in Unit 3 as well. This looks like a KSP problem, basically. And your equilibrium expression is going to look like this. Kb equals calcium ion times hydroxide ion squared. Okay, so a tip here for the Arrhenius bases, some metallic hydroxide, it's going to be easier if you don't include water. All right, so it just makes it a lot cleaner, a lot nicer, and much easier to write the expression for everything. Okay, Sometimes I like to even write the acidic dissociations without water. As you can see, I did that here on this slide. Okay? So you can take, I think these are in your packet, you can take a minute and write the dissociation equations for these. So recognize if it's an acid or a base, and you could go through the dissociation if it's an acid. If it's a base, you want to add water to it, okay, unless it's an Arrhenius base. Then you just want to do your regular dissociation, okay? But if it's not an Arrhenius base, Arrhenius bases, it would be a Bronsted base then, right? Bronsted bases are going to be proton acceptors. So if you add it to water, you can show easily how that proton is being accepted by your base. Okay? So you can do that. We can go over them in class, and we'll take it from there. The last thing to wrap this up for today is just an intro to the acid-base equilibrium problems. These are really no different than IC table problems, except we have acids and bases. So I'll get you started with the first one here because it's a little bit different. It says 12 molar is the most concentrated HCl can get. What's the hydrogen ion concentration in 12 molar HCl? The main thing you want to do here for all of these, and it's what I'm going to go over a million times in class, is you want to start with your dissociation equation. You have to get an equation before you do anything else. So HCl yields H plus Cl minus, okay? So the thing you want to recognize here then is, what is HCl? Well, HCl is one of our strong acids. So it's going to be complete dissociation, all right? So we have our initial value was 12 molar, and this was 0 and 0, right? And then at equilibrium, since we don't really need an IC table here, we know what the change is. This is a strong acid. It'll completely dissociate, so there's none left at the end. So we're going to end up with 12 molar hydrogen, 12 molar chloride. Okay, so the answer here is, what is the hydrogen concentration, hydrogen ion concentration in 12 molar HCl? And the answer is 12 molar. Easy. Okay, so strong acids work like this. Make sure you recognize if it's one of the top 7 strong acids first, before you do anything else. If you have something like this, though, it's not the same. Okay, we have acetic acid and we have a low Ka value, so we need to make sure we write our dissociation equation, recognizing though this is a weak acid. All right, so acetic acid is HC2H3O2. I'm just going to write that as HA. I'm being lazy here, and I'm using my mouse to do this instead of my touchpad. So HA, the equilibrium, because it's a weak acid, makes H plus and A minus, which will be your acetate ion. Okay, gives you Ka value, and it says what's the concentration of the ion hydrogen at equilibrium if the equilibrium acetic acid concentration is 6 molar. Okay, so I don't have an initial value here, okay, for my IC table. I don't have any initial values. This is something, I don't know what it is. This is 0 and 0, obviously. Some change is going to occur, like you do the rest of your IC table, I, C, E, E, right? And at equilibrium, this HA is 6 molar. Okay? What is H plus and A minus, though? It's not really a shortcut here, but use what you know from the problem to figure this out. Basically, you had HA put in water. See how you had none of this, none of the products initially? You had 0 molar concentrations of H plus and A minus. So what does that mean then? That means when HA does dissociate, it'll dissociate into H plus and A minus equally, right? So you're going to have, like, whatever you end up with at equilibrium, the change would be plus X, so blah, blah, blah. Your E value in the IC table is X. Okay, so you're going to make X molar hydrogen, X molar acetate ion. So set up your Ka expression. Okay, Ka equals, right, H plus times A minus over HA. And then you have Ka right here, plug it in. You have HA, plug it in. You have H plus and A minus as X's. That's easy to solve using some algebra. Plug it in and go from there. Okay. Sometimes it's not as straightforward as this, and you actually have to complete the rest of your IC table. The thing here is you need to start with your equilibrium expression, okay? your dissociation equation, and then work it through from there and see what's given to you, initial values or equilibrium values. All right. The rest of this is just working on practice problems. We can do some of that in class. If you have any questions, just let me know. Thanks, guys.